Thanks, Volker. It's great to be here. Big fan of the seminar series. And I also think the YouTube channel is a fantastic resource. So hopefully I'm not crashing it with adding another video to it. I'm excited to present this paper. It's on a topic that some of you might find interesting, but it's also interesting because it's kind of a new way of how we tried to organize research. So it's actually an experiment where we blocked all of our calendars, everybody in my group, and did nothing but work on this for 2 weeks. And of course, we didn't finish it in 2 weeks, and there were a couple more night shifts to get the draft done. But it's actually an experiment on how to do research differently, perhaps inspired more by engineering and natural sciences and so on. And so verdict is still out. I liked it. Don't know about my co-authors. Definitely a different pace. Yeah, so that's kind of the background to this. All right, so let me start by motivating this broadly, which I don't think I need to really do in this audience, but I think it's clear that data is a key input to AI, and there's essentially three ways on how you can think about this in terms of different types of data sets. Probably the economically most important type of data in our current days is behavioral information, actions, reactions, usage patterns that come from web browsing data or from app user interaction data. And all of this goes into online ads. And that's why I think it's probably the economically most important thing. Then you can also think of sensor measurements from physical devices, Internet of Things, Industry 4.0, these kinds of devices that will largely, of course I'm oversimplifying, but largely will go into robotics applications. And then there's this whole universe of data that has been flying around for quite some time now, and we haven't really thought about it as data, at least at the larger scale, until generative AI came around. And that's human-generated content, roughly speaking: text, image, sound, video data, these kind of things. And today I want to focus on that category of data when I talk about data and AI training data in this paper. So I think the focus of what we're trying to do is to think a little bit about the stock versus the flow of data. And if you think about the existing content, sort of the vast stuff that's available online, that's huge amount of information: text, image, video, audio data. And much of the stock was actually created before the dawn of AI. And so that's why you have a lot of things. And we don't really need to worry about this, or don't need to worry too hard about this from a regulatory perspective. If there's no need to update training data, if essentially everything that's online can be used and is useful for AI training purposes. But then, at some point, the stock might be exhausted. And then the flow of data becomes more important. And even more in dynamic settings, the stock of data can get stale, and sort of what was relevant yesterday is no longer relevant today and will be even less relevant tomorrow. And therefore, it's important to not only think about the stock of data, sort of these huge amounts of data that we already have flying around on the internet, but also sort of think about the flow of data and how we can make sure that there's a continued flow of data if we worry about training data quality, for example. The interesting part here, of course, is that the flow of data is endogenously determined. So people make decisions about which data to create, which content to create, that sort of ends up as data online. And that's going to be a function of economic incentives and, of course, also of regulation. And I think that makes the whole discussion very interesting to an economist, because in this whole technical discussion, all of a sudden, sort of social science plays a role, and sort of market design maybe plays a role, regulation plays a role, and so on. So what happened with this rise of Gen AI is that some human creators were not happy with their training data being used. And all of you have seen these high-profile lawsuits, the New York Times suing OpenAI and Microsoft over copyrighted work, Getty Images, which is a stock photo company, suing Stability AI, which is a company an open source that provides an open source platform for image generation algorithms. There's also this anecdote of a German photographer who tried to get one of his photos removed from an AI data set, and then they had clever lawyers and essentially just sent him an invoice instead. And so, a lot of legal action on this, and this tells you that it's absolutely unclear what the situation really is. So nobody really knows whether data is copyrightable. This type of data is copyrightable, and then there's also vast differences across countries, and sort of just a big legal mess. That's why you have all these lawsuits for courts to decide. But even if this is decided, the open question would still be, what about the dynamic incentives to create works or / data points in the first place? So what regulation can do is to say yes or no. You can use the existing data that's already there, the existing text, the existing images, the existing videos, and so on. But if that's, let's say, we would have some kind of carve out in copyright law, what would happen to your incentives to create new things in the first place, right? And I think that's a question that is perhaps the more interesting, perhaps the more important one, but definitely less talked about. And this is what we want to focus on in our paper. So we're essentially going to tackle two research questions. How do creators change their behavior if their works become AI training data? And then what are the implications for the training data quality? So it's essentially a question of quantity and then a question of quality. We're going to use data from a stock photography website called Unsplash, and I'll give you more information about Unsplash in just a second. What's nice about this setting on Unsplash is that we have a pretty neat identification strategy, because Unsplash released a data set of 25,000 selected images, which are randomly selected images for AI research. Essentially, they made some of the images that are on the platform available explicitly for AI research and others not. And then we're just going to do a standard diff and diff, where we compare the behavior of contributors whose works were included in this data set versus contributors whose works were not included. And we're going to compare the behavior along a variety of dimensions. How long do you stay on the platform? How often do you upload to the platform? What kind of images do you upload to the platform? And so on. And just to foreshadow the results, we'll see that treated users are less likely to stay on the platform. They delete their accounts more often than non-treated users. And they're also less likely to upload new content. So the flow of data is diminished. And then we're also going to apply some natural language processing to understand a bit what is on these images that are continued to upload compared to images that are already available on the platform. And we'll see that the variety or novelty, and I'll explain exactly how we measure these concepts, decreases compared to the existing content. All right, so let me talk a little bit more about the empirical setting. So the setting is Unsplash, a stock photography website that hosts user-generated content. So it's a bit like YouTube. Anyone can upload. Anyone can upload photos, and you can upload illustrations. Currently, they have about 360,000 contributors, about 6 million photos, and of course, growing over time. Unsplash is also pretty successful. So it's in the top 5 of photography websites globally, 30 million visits per month. And combined, the images that are hosted on Unsplash have been viewed 1 trillion times. So I don't know what trillion means. It's just a very large number. Okay. Out of these 6 million images that are on the platform, a team of human curators selects images to be featured prominently. That's what you see on the screenshot here. So they pick on a rolling basis images that are shown on the front page, images that are shown if you click on one of these categories here, and sort of make you, help you a bit in finding the nicer of all these images that are uploaded. In addition, images are also tagged with keywords. So if I upload an image, I can specify keywords manually, just what describes the picture best, or what I think will help users find my picture most. But they also apply a computer vision algorithm to all of these uploads, and then sort of have a host of automatically tagged keywords in there. So this one would probably say tree, it would probably say sun or solar eclipse, and so on. And then these algorithms have become pretty good. So for every image, we have user-generated keywords and these automatically generated keywords. And then the catch about Unsplash is that all images are free to use for commercial as well as non-commercial applications. So the moment you upload your images to Unsplash, you'll essentially make them available in something that's very close to Creative Commons 0. So a very open license. So essentially anyone can use the images for whatever reasons. It's even more open than Creative Commons 0 in the sense that you cannot revoke the license for an image. So it's the sort of the openest license you can think of, right? So that probably already tells you that people who contribute to Unsplash are a bit special people, because they literally waive all their copyrights for images that they upload. And by definition, all the images are for commercial as well as non-commercial purposes. All right. Now, what happens in the summer of 2020? Unsplash releases AI training data sets. So not images, but meta information about these images. And they make a big fuss about this and say, now you can access the world's largest open library data set. And essentially release this data set in 2 flavors, one that they call light and the other one that they call full. Full is essentially the entire catalog of images that they have available. So at the time, I just talked about 6 million or so images that are on the platform at the time in the summer of 2020. This was 4.8 million images. And then the light is a data set that anyone can download. It has 25,000 images. And the data set itself, which is again just meta information, it tells you the name of the photographer, it tells you these keywords that I just talked about, it tells you information about the pixels that are in the images, what are the most frequent colors in these images, things like that. This data set is the light version of this is free for commercial as well as non-commercial research, and then or usage. And then the full data set, you see that there's a button where you have to request access. So this one will be restricted to only non-commercial usage. So if you click on this button, there will be a form. You have to answer questions, and then there will be a manual process with which Unsplash decides whether you will get access to this full data set. So as someone who went through this process, I can tell you that it's not easy. It will take some time, and they really insist that you essentially have to swear on the Bible that I will not use it for commercial purposes. Okay. So for you, the big difference, or sort of what you should have in mind, is light data set. Anyone can download it very quickly. You can do whatever you want with it. Full data set, way more complex, but it's more data points. Okay. And if you downloaded the full data set, then you can only use it for non-commercial projects. Okay, so then the next question is, what determines being in the light data set? And the short answer is this guy, and the long answer is this query here. So this essentially tells you that an image that is in the light data set is nature themed, is curated. Curated means it has been selected by one of these human editors, and it's above a cutoff of how confident the computer vision algorithm is that actually nature is depicted on that image. Okay, so the reason why they chose nature-themed images is, I think, because they wanted to avoid that you have persons on the picture, and then adjacent rights of persons. So they wanted to be very, very far from that, and so you essentially have mountain ranges, animals, oceans, things like that. And then why did they choose the curated pictures? So I had the pleasure to interacting with Tim a bit, and then he explained that it's easier. He said it's easier on the eye. So these images are just nicer to look at, higher quality. That's why they went for the curated. And then this 0.9 confidence cutoff is just something that they chose. Okay. So earlier I said randomly selected. So just from looking at this, it doesn't look like it's randomly selected. So there's no random sorting or so. What it does actually, it's still random in the sense that the way the data set is sorted from these different databases where all the different information is being pulled from depends on sort of the execution plan of the database system. I fell into a little bit of a rabbit hole on how database systems work. And so literally in the documentation of the database system that they used at the time, it says you don't want to do what they did here because it's not going to be replicable. So every time you rerun this query, you'll get a different order and a different subset of results. Which is of course not great if you want this to be replicable. If you want this to be more or less random subset of whatever is there. If you are an empirical social scientist, then this is great news. If the documentation of the database system literally tells you, it's not going to be reliable, you get random sort order. Then for me that was I was quite happy when I read this. Now, of course, I can tell you whatever I want. I can make up any stories. I think it's probably more interesting for you if I show you some data that tells you that the sort order in this data set is essentially random. So what I did here is looked at the 25,000 images that are in the light data set, and I'm trying to explain the order in which they appear in the light data set. And you see that the image popularity, how often it has been viewed, how often it has been downloaded, and so on, doesn't explain anything in the search popularity. In the order in which the image appears in the dataset, whether it has how many keywords a user has attached to it doesn't explain anything. How old it is doesn't explain anything. All the variables that I can put in here don't explain a lot. If you look at the R squared, so it's essentially so much variation in there that I cannot explain with these variables. The only thing that explains it is the score, the confidence score of this computer vision algorithm that tells me how likely does the algorithm think it is that the picture actually depicts the concept called nature. And that one predicts it, and that also should predict it, because if you look at the database query, we are looking at only images that have the tag or the keyword nature, and if the confidence is above a certain threshold. So if you're 90% confident, then you should be in the data set. If you're 95% confident, you should be even more likely to be in the data set. And that's also what we see here. All the variables that could potentially sort of make this problematic from a social science perspective, meaning that there would be, for example, user behavior that made it more likely that an image is in the data set, for example, because I'm a very good photographer and therefore my pictures are more likely to be used for this project. all of these variables essentially don't explain anything. Okay. Ideally, I would, of course, like to look into more than 25,000 images. Ideally, I would like to see the query of 50,000 images, 100,000 images, and sort of compare the sort order to other data sets. But I only have the 25,000 that they pulled at the time. Okay. So in that sense, within the light data set, I'm pretty confident that I can tell you it's. I don't find any variables that might be determined by human behavior that explain whether an image is ranked higher or lower. What I can tell you is whether the 25,000 first image is substantially different, whether the next 25,000 images would be substantially different in this regression. I can tell you. Okay, but I'll talk about this in just a second. Okay, what kind of images are in the training data set? This is one example that's actually in a training data set. So earlier I said it should be easy on the eye. Nice, these are really high quality images. They're very, if you don't know the website, go and look at a couple of images there. It's really nice photos. Okay, so identification and methods. We're going to compare treated users to control users. Treated users are, that's the easy part. These are all the users that have at least one image in the light data set. Out of these 25,000 images, 8,298 users belong to those images. And then we're going to define a control group that looks just like the users that are in a treatment group. So first of all users without images in light. That's the other easy part. Then images that were uploaded before the light data set was created. That's also easy. Because essentially what we want to do is we want to make a control group of users that at the time when the light data set was created. So of course all the images that were uploaded later are irrelevant for that, and all the users that were not even part of the Unsplash platform at the time when the light data set was created, they're also irrelevant for this exercise. And then we look at all the images or all the users that have at least one curated and nature themed image with the confidence score of greater than 0.9. So essentially what we're trying to do is rerun this database query and select all the images that are left out of this limit of 25,000. So all the rest, but the same criteria. Okay. And it turns out that these curated nature theme with confidence score greater than 0.9 is fairly restrictive. And so we end up with 3,754 users in the control group. So we try to make this as comparable as possible. You can also think of other control groups. In the paper, we have a couple of robustness checks. So perhaps the most, the easiest control group you could do would be just anyone who has 0 images in a light data set, and essentially just treat or compare to those users. Essentially, we get the same results. So this doesn't matter too much. And perhaps slightly more elegant, slightly slightly nicer econometrically. All right. Hopefully that's sufficiently clear that I can now jump into the results. So that's first I want to talk about user behavior. So this is looking at all the users that are in the light data set that have at least one image in a light data set, so only the treated users. And I'm going to compare their behavior after the light data set was released over a period of 2.5 years, and just follow them over time and see, compare them to sort of the control users, and understand how likely are they to delete their accounts. So how likely is it that I can find the same user still uploading 2.5 years after the light data set was released? Okay. So what we find here in columns 4 and 5 is that for these treated guys, you have a deletion rate of about 5%, which is 1 percentage point higher than what you usually get. So the usual deletion rate is about 4%, okay, over this time period of 2.5 years. Now, if I look at the images, so not the users, but the images themselves, here we find the opposite. That's actually a lower deletion rate, 7% versus the usual of 9%. So if an image is selected to be in the light data set, it stays on the platform longer. Okay? Now, let's look at a before and after analysis. In what I just showed you, this was only the after period, because of course we don't have a before period. Now here there's a before and after analysis, a very standard difference in differences specification, where we're going to look at the number of images that are uploaded by user I in week T, and then treated will indicate whether user I was included in the light data set. And then we're going to have time-fixed effects, user-fixed effects, and we're going to be interested in this difference in difference coefficient, this delta here. And we're going to make a panel structure where every user, we observe every user in every week. And if there's an upload, then we count the number of images that are uploaded in every week. And if there's no upload, we're just going to put a 0. So essentially, we are building a panel, a balanced panel of all the users, these 8,000 treated users and 3,500 control users. Okay. So the underlying model of this is that a user decides every week whether and how much to upload. Okay. All right. So this is the number of uploads. Comparing the treatment group to the control group. So what I'm showing you here is the difference between the two. So this is essentially the delta coefficient in the difference in differences model, but estimated for every week. And you see in the before period, it kind of fluctuates around the 0. So there's not a statistical difference between the treated and the control users. And then in the after period, after the light data set has been released, you see this immediate drop, which stays at around -1, which essentially means roughly 1 less uploaded image per month. Okay? So that's every time you see such a plot in a different diff paper, as an author of a different diff paper, this is your happy moment. This is what you want these plots to look like, right? So what I just showed you is the number of uploads. So if I just do the period before, period after comparison, then you get this 1.1 coefficient, which translates into an effect size of about 40% reduction. We can also look at a dummy variable that just tells us whether there is an upload at all in a given week. So here you can think of this as the intensive margin. Column 2 would be the extensive margin. And here we see a reduction of 30%. And then also, the logarithm applied to 1+ uploads. Of course, there will be a lot of zeros. Not everybody's active in every time period. And that will also give you an estimate of 30%. And then some of you might wonder about other potential econometric models that we could use, Poisson, negative binomial, these kinds of models. We did all that as well, and there's a lot of tables in the appendix that essentially show you the same thing. Okay, so that's sort of the quantity results. About 30 to 40% less uploads of these treated users compared to the non-treated users. Now, perhaps slightly more interesting is how does the type of image change? Of course, conditional on these users that are still active on the platform. In one of the first tables I showed you that these treated users are actually more likely to delete their accounts. And then also conditional on the overall number of uploads being lower. So first way to look at sort of whether the type of content changes is to essentially just look at the categories that we already have. Is it a nature image? Is it an image that will eventually be picked up by the human editors to be curated? Or is it a nature and curated image? And so you see a 30% reduction in nature images, 60% reduction in curated images. If you believe that the human editors do a good job at finding the high quality images that are uploaded at any given moment, that's twice the amount of reduction for the nicer images, and then the nicer nature images even a 70% reduction. Okay? So that's of course only a first order approximation of what quality may mean. Let me introduce sort of a conceptual kind of framework of how you can think about quality. Let's think about variety in terms of the information about distinct concepts that can exist in a data set. If you're familiar with econometrics, then you can think of this as a cross-section or the number of firms in a panel data set. That gives you variety. And then there's also novelty, which is the updated information about the same concept. Think of this as a panel data set as enlarging the time series. So for the same firm, you observe multiple years in a row. And so with every year, you get more novel data points. Okay? And with image data sets, both may matter, because you might want to have images about various different concepts, a tiger and a lion, and not only tigers. And then novelty, even if it's about the same concept, might also matter if the word changes in between. And given that I'm virtually presenting in Berlin, this is probably the most fitting explanation for this idea of novelty. This is the Brandenburg Gate before 1990, and then the same concept 20 or 30 years later. And so as the world evolves, you sort of need continuous updates, similar data points of the same concept in order to be able to have continued algorithmic performance. That's kind of the idea. Okay. So variety, novelty, these are the two quality aspects that we want to focus on. How do we measure this in the context of Unsplash? So we try to do this with an NLP approach using this user-specified keywords. So if I upload an image, I'll write down, this is the Brandenburg Gate, this is Berlin, this is a street, and so on. And on average, I think I have a slide somewhere, but on average, it's roughly 10 user-specified keywords per image. And we're going to use this to then understand sort of what is the contextual similarity of images that are uploaded versus all the images that already exist on the platform. And then you can do this in various degrees of fanciness. You could only look at the keywords. We go one slight step in terms of fanciness further by not only looking at the keywords, but at vector embeddings, which is essentially telling you sort of what sort of the in the natural language the context of a word. So if you say Berlin, then it would also sort of relate it to similar concepts such as capital, such as Germany, and so on. So it's more than just the keyword. So essentially, we're transforming keywords into a large matrix of embeddings and sort of related concepts. And then I do this essentially for all the images that we have on Unsplash, and then measure how similar each new upload is relative to existing keywords, and then also count the number of existing images that are very similar to a new upload. And by very similar, I'll just specify a cutoff, and I can show you results with different cutoff points. Actually, just a way to get at this novelty. So far, so clear, I hope. Here are some pictures and how you can think about that. So this is the average similarity of an uploaded image before and after the light data set was released, of in blue treated users and in black control users, you see that there's kind of a natural tendency of things to get dissimilar over time. So new things are uploaded, the world changes. That's kind of the Brandenburg Gate example. But for the treatment group, sort of things stay more stable. And then in terms of novelty, the number of very similar images, also there's a stronger decrease in the control group. Sort of the natural tendency of what people would upload decreases, so you get new things added over time, versus in the treatment group you get less new things added. There's almost stable amount of very similar images. Okay, so here's the regression version of this. I'll spare you the details. You can just think about the effect sizes of about 5% increase in similarity and about 30% increase in the number of very similar images. So what matters here is that we get quite different results if we put user fixed effects. That tells you that it's essentially what is important here is to again take into consideration that certain amount of users essentially stops uploading, and those that continue to upload upload more boring images, things that are more similar and less novel. And once you don't take that into consideration, the effects are slightly smaller. Okay. I'll have 2 or 3 more slides to just talk a little bit about the time effects. This is in terms of Gen AI in June 2020. This is Stone Age essentially, compared to what we're used to now. You see the effect essentially drops down after August 2022. What happens in 2022 is this is when the image generation AI things start to become really impressive. There's an article in the New York Times that's titled "We Need to Talk About How Good AI is Getting," and a few of these very powerful models are being released. And essentially what you see is that there's an even stronger decrease after August 2022, perhaps when these photographers realize, okay, my training data is actually going to help algorithms that are becoming pretty good. In a regression format, you see that this leads to an additional 0.4 less uploads in the period after August 2022. And then if we look at differences in treatment intensity, those photographers that only have one image in this data set of 25,000 versus those that have multiple images in there, you see that for the multiple image treated users, they react much stronger to the treatment. Okay, so if I'm treated more, if more of my images end up being used for these algorithms, I'll upload even less. Okay. Now you could say, well, is this only true for Unsplash, or do people just stop being photographers, stop uploading content anywhere on the internet? And that's a bit of a tricky question, but thankfully on Unsplash, a lot of photographers actually also share their Instagram handles. And so we can find them not only on Unsplash, but also on Instagram. So here's an example. Jason Lowe has on his or her Unsplash profile, there's directly the Instagram link. And so what we did, we went to these Instagram profiles and also checked what people are uploading to Instagram. It's a bit more difficult than you would think to get data from Instagram. So I don't have as much data as I would love to have, but for the purpose of this exercise, I think it's sufficient. You'll see that out of those creators that we observe on Unsplash as well as on Instagram, the decrease in uploads is only happening on Unsplash, and the behavior essentially doesn't change on Instagram. So it's not that creators seem to stop creating overall, but they stop creating or uploading to Unsplash, which is quite interesting because the license policy of Instagram is not very different. It's not as clearly specified, but it's certainly also not it's not a stock photography website where you can make money by uploading images. Kind of the same concept. Perhaps you're a user of Instagram because you want to sort of get known to the world as a photographer, as much as you would do that on Unsplash. But the treatment effects really here only apply to Unsplash. And then I don't have a table for that. I just wanted to mention this. At some point, Unsplash also introduces a paid program, what they call Unsplash Plus, where you can sell your images, and we'll actually see a 3 times higher uptake of this paid program among the treated users compared to the control users. So there seems to be some kind of substitution going on. All right, so let me speculate a little bit about implications for AI output quality, and then talk a little bit about what I think could be interesting policy implications, and then I'll shut up and look forward to our discussion. So, of course, in all the results that I showed you so far, I can only talk about mostly I can only talk about quantities. I can't really talk about quality. I made it sound like I talk about quality when I talked about variety and novelty, but I can't really touch on the most important question, which is, if there's now less training data available, how does this change the output quality of an image generation algorithm? That's essentially what I would love to know. And so what we did here is we essentially went to the technical literature and tried to see, can we find some estimates in there and relate our estimates of the quantity reductions to sort of quality outputs. And the first one is easy, size. There's a few papers now that show that algorithmic performance increases when you have a bigger data set. And if we just triangulate kind of and these are, by the way, well identified, empirically well done papers. So if you look at the sample size reduction of about 2%, which is what we find on aggregate, sort of these 30% that I was talking about translate into 2% on aggregate, you get about 1.5 to 2% reduction in output performance. When you think about novelty, there's a range of nice experimental papers in computer science that look at the geolocation problem, which is essentially, what's on the picture in terms of geolocation. This is Berlin. And then you try to predict whether it's an image that depicts Berlin in images where you don't know the geolocation, which is more or less also kind of the example that I gave you. And in these papers, you will also have nice estimates that we can work with, and so a reduction in novelty, sort of less new pictures of Berlin. Of about 12 to 28% would translate into a 4.5 to 11.5 reduction in output performance. And then lastly, variety. This is more difficult. So we looked a bit into the recent technical literature that talks about using synthetic data as a substitute to real data that might have copyright issues, for example, attached to it. And so synthetic data essentially means using AI-generated data, AI output data as AI input data later on. And then sort of these papers estimate, how much worse algorithmic output gets as you feed it AI-generated input. And then here the thought experiment would be, AI-generated input data, that's very similar input data. That's something that is already sort of learned from existing data, and it might be relatively similar to what I already have in the data, compared to at least within the thought experiment, compared to fresh updated data from the real world, where also the real world has changed. And if you want to believe that, then you can use these estimates to essentially relate our increase in similarity of about 5% that we find to a quarter to 1.5% reduction in output performance. So I think these are quite substantial effects if you can sort of believe my speculations about the output quality. But if you don't believe them, then I think still the quantitative results, just the number of, or the decrease in the number of uploads, already quite substantial. So where does this leave us? I think the interesting policy background here is copyright, where data can be subject to IP protection, and it's not so clear whether copyright law needs to adapt to this. There's a nice paper that essentially compares the law of more than 200 countries, which came out in Science, that where a lot of legal scholars that are on this paper essentially conclude that outdated copyright laws around the world can hinder research because it's absolutely not clear whether and how much you can use data. And of course, this leaves us with a policy trade-off, where we want to trade off AI innovation versus the interests of rights holders, and of course, and that's the important part here, their dynamic behavior. And so far, we didn't have any empirical evidence to inform and guide policy. So I'm hoping to contribute something here. And I think it's interesting that even in our setting, this Unsplash setting, with this very open license, where copyright actually doesn't factor in directly, we see this sizable change in behavior when human work is put into AI training data sets. We see that a change in quantity and a change in what I call quality can affect the value of training data and perhaps the AI output. And then that leaves us the questions of, do we really want to open up copyright for AI, for example, fair use or research exemptions? Because we might end up in a world where we have low quality AI outputs and low quality human works. If people produce less works and less interesting works. And so I think that's food for thought, and I'm looking forward to the discussion. Thanks so much for your time.